All right, let's do some paper and pencil comprehension exercises here. So for all three of these exercises, we're going to do the same thing. We're going to find the value of z. We're going to find the slope of z with respect to x, and we're going to find the slope of z with respect to y. So the three different points that we're going to do all three of these steps at are where x is equal to 3 and y is equal to 0, where x is equal to 2 and y is equal to 3, and finally where x is equal to -2 and y is equal to -3. All right, pause the video here and take a crack at those because we're going to go over the solutions. All right, so for question 1, we've got a point where x is equal to 3 and y is equal to 0. So first things first, figure out what z is equal to at that point. Well, we just use our formula for this curve. Z is equal to x squared minus y squared. So x is equal to 3, y is equal to 0. 3 squared is 9, 0 squared is 0, 9 minus 0 is 9. So now we know that our point is at this location. So at that location, what is the slope of z with respect to x? Well, we can use our del z del x equation, which is 2x, and substitute 3 in for our x. That's 2 times 3. And so the slope at that point with respect to x is 6. The slope of z with respect to y, we use our del z del y equation, which is -2y. We substitute in 0 for the y, and that gives us a slope of 0 at that particular point. Nice, so looking at our chart here that we already created and adding a new point, which is this point right here. So it's a point where x is equal to 3, y is equal to 0. What's z equal to? It's equal to 9, and it has this slope with respect to x at least of 6. So those are all the things that we just calculated on the whiteboard, shown here in graphical form. All right, for question 2, we'll consider this other point where x is equal to 2 and y is equal to 3. At this particular point, what's z equal to? Well, we can use our same formula as before, plug in the 2 and the 3. That gives us 4 minus 9, which gives us -5 for the z coordinate for this point. So there's a point on this curve at 2, 3, and -5 for x, y, and z, respectively. What is the slope at that point of z with respect to x? Well, we use our 2x formula, plug in the 2, and that gives us a slope of 4. What's the slope of z with respect to y? Again, same equation, -2y, plug in the y, and that gives us a slope of -6 at that point. Again, let's take a look at our graphical representation. And so now we're at a point here where x is equal to 2, and you can't see that, but it's true, and you can prove that to yourself from the code demo earlier where we created this chart. So x is equal to 2, and at the point where y is equal to 3, we see that z is equal to -5, and it has this relatively steep slope of -6 with respect to y. And we can't see from this two-dimensional representation what the slope is with respect to x, but we know it's 4, and you could, if you want to, go look in the GeoGebra 3D visualization to have a look at what that is like at that particular point. All right, in our third and final exercise here, a point that we haven't tried to plot yet, but you're welcome to try plotting yourself using some of the functions that I've already created for you in the Jupyter Notebook we're working through. We are interested in this point here where x is equal to -2 and y is equal to -3. What is z equal to at that point? Well, as usual, we can use our equation of the curve here, plug in the x and y values, and that gives us a z of -5. So we have a point in the curve at x is equal to -2, y is equal to -3, and z is equal to -5. At that curve, what is the slope of z with respect to x? Well, we know it's going to be 2x. 2 times -2 is -4. And the slope of z with respect to y, that's -2y, as we've seen before. Plug in the -3, and that gives us a slope of 6 at this point. Determining partial derivatives by hand, like we did on the whiteboard, or you did it with paper and pencil perhaps, is useful for understanding how calculus works. In practice, however, autodifferentiation enables us to do so more easily, especially if there are a large number of variables. For example, we can use the PyTorch AutoDiff library to calculate the slope of z with respect to both x and y at any given point x, y, z. So we create, let's say, where x is equal to 0 and y is equal to 0. We create two scalar tensors for x and y respectively. And because we are going to be calculating the slope with respect to these variables, we need to turn requires grad on. We need to set that argument to true. And then we can just perform a forward pass. So we can use the function that we already had, which we set to z is equal to x squared minus y squared. And at that point, z is equal to 0. And if you may already have known that from some of the curves we've been looking at, that where x and y are equal to 0, our curve is also equal to 0 for z. And now we can use AutoDiff to go backwards, to calculate gradients backward from z. In this case, it's just going to go to x and y and calculate the gradients at this point for z with respect to x and y. So as we should already know from our exercises above, the slope of the point 0, 0, 0 is 0 with respect to both the x and the y axes. And you should know that from our del z, del y, and del z, del x functions that we already determined by hand earlier. So, by using PyTorch, you can circumnavigate manually calculating what partial derivatives should be and simply rely on this computational library to do it for you. So now, as an exercise, you can repeat the most recent pencil and paper exercises using this PyTorch code here. Or if you're feeling really adventurous, you can try it with TensorFlow 2. So as an example, if you want to calculate for this first point here, one thing that you're going to need to do is restart the notebook. So restart the runtime. And then you can click on this markdown cell here and run all the cells before. And once that completes, because of the way that gradients get stored in memory, you're going to need to reset the notebook when you reset these variables that we're tracking gradients on. But so now, if you want to solve for z and the slopes at the point where x is equal to 3 and y is equal to 0, you can substitute a 3 in for x and carry through. 0 is still a 0. Remember, we're going to need floats here in order to make this work. Our forward pass is the same as before. It comes out to 9, which is the same as we got with paper and pencil. We perform automatic differentiation, and now we can find the slope of z with respect to x and y, which, as we knew from the paper and pencil exercises, would come out to 6 and 0. So yes, so the same answers as we had before, 9, 6, and 0. So you can restart the runtime and take a crack at those yourself, particularly paying attention to trying to understand what's happening and what you're calculating in PyTorch here. Nice, so you should now have a basic understanding of partial derivatives, how to calculate them with paper and pencil or a whiteboard, as well as using auto-differentiation in PyTorch. And so up next, we're going to make things a step more complicated by looking at partial derivatives of relatively complex geometrical shapes, certainly more complex than the simple function of the curve we've been working with so far.